Hi, Berkeley High students. It's Mrs. Francis. I'm happy to be with you today. We're going to talk again about the quantum mechanical model. We did a short little video one to talk about how that model describes the location or the probability of an electron being in a specific location, that it's a statistical model based upon mathematical equations. I went into the lab this week or into my classroom and got some balloons out of the lab and made a couple of models for you. So I want to remind you that the first sublevel that we looked at was a sphere. And that sublevel only has one orbital, and each orbital is going to be represented by a box because it's difficult to draw a sphere. And that sphere would surround the nucleus, which would be at the center there, and that each orbital would hold up to 2 electrons. Take a look at this video.
I'm going to first just start with an ordinary balloon, and I want to show you the s orbital. Now think three-dimensional. A circle is flat. But if I blow up this balloon, I can get a sphere-like shape here. Imagine that you can have up to 2 electrons in this space right here. And so in the center of this space would be the nucleus. Nucleus means center in Greek. So I can have up to 2 electrons, and they're moving about. It's difficult to know how fast they're going and exactly where they're at. That's what Heisenberg said. And so these 2 electrons are moving about constantly, like 2 toddlers who ate a bunch of sugar. And so moving about, moving about, moving about. Okay, that's the 1s. Now, outside of that, we might have the 2s. So give me a moment and let me show you that. All right, praying I don't have this pop. All right, this is the tricky part. Makes me cringe. All right, now I have a bigger sphere, but inside, can you guys see that there is a smaller sphere? Now, if I had the ability, and maybe if I were a magician, I could get that smaller sphere to be centered in here. But this is a balloon, and that's one of the downfalls of analogies. They don't always hold exactly true. But there are 2 electrons represented in the inner sphere, and then there could be 2 more electrons that are represented in this outer sphere. Now, the outer sphere space goes all the way from the nucleus all the way out to the edges here. Now, what's different about our analogy compared to what's really happening with electrons is these balloons have a skin, and it looks, oh, like, yeah, that stops the electron. No, there's no skin in an atom. Okay, there's no balloon material to stop it. They run out of energy. Okay, they don't have enough energy to get to the next place. Now, what's really amazing is when we get to the p orbital. You'll see that in just a few minutes.
All right. So the second sublevel that we mentioned last class was the p sublevel. I call that the petal shape. And we noted that there are 3 orbitals. And so we draw 3 boxes, 1, 2, 3. And it's got an X, a Y, and a Z component. Take a look at this video.
Okay, so you remember the spheres? 1s on the inside, 2s on the outside, and then we got 3s and 4s, and we just keep getting bigger and bigger spheres, which means that the electrons can move farther from the nucleus. But we've got other shapes, and we just talked about the p orbital. So the p orbital is my favorite to make. It's going to stem out of the center. In other words, the location of the electrons can be from very close to the nucleus all the way out to the edges of this balloon. But it's not just one balloon. It's going to be 3 balloon structures. So let me explain. So this is our first p orbital. It can hold up to 2 electrons because remember, every orbital can hold 2. It could have 2 on this side, it could have 2 on this side, it could have 1 here and 1 here. Just depends. Nucleus is in the center, and this would be kind of coming out of the middle of this if I could make this all come together. All right, now, just like in a graph, this one has a name P sub x, meaning it's like the x-axis. Okay, let me get the second part now. Okay, there's one. Again, it looks like there's two parts. Holy moly. All right, I might have to try a different balloon. Okay, I'm going for a blue one. I wanted to use the same color, but I think you'll get the gist. Okay, so now, looks like two parts, but there really aren't two parts. This is one part, stemming again. Now, it looks a lot like this, except its orientation is up and down, like the y-axis on a graph. So this is P sub x, can hold up to 2 electrons. P sub y, which can hold up to 2 electrons. 2 on this side with 0 here, or 2 on this side with 0 here, or 1 here, or 1 here. All right, let's get to our final piece. This is a piece that I really want you guys to see. All right, one. And now I think you're getting the gist that, oh, that's a strange looking balloon. Woo, didn't work. Okay, I'm going for a third. Okay, here we go. You guys, I love this. It's like live science. Oh, that surprised me. I wasn't expecting purple. All right, so now this is my last part, and it's, again, holds up to 2 electrons. This is the third orbital. All orbitals hold 3. And now I've got my x and y. I've got my third part, which is now the z. So the z is coming out at you towards the camera, and then my green balloon is going back into the board. This is the P sub level here. We've got 3 orbitals, 1, that's P sub x, 2, that's P sub y, and then coming in and out, the P sub z with 2 more, 2, 4, 6 electrons.
So it turns out I'm not really that great with balloons, but hopefully that gave you a little bit clearer idea about the spaces that surround the nucleus in which we might find an electron. They're 3-dimensional spaces. So last class, or last video, we also took a look at the periodic table, and we found out that the periodic table is going to help us to describe the location of each and every electron in every single atom. And we've divided it into 4 sections: the S block for that sphere, the P block for that petal shape, D, and F. And so this is going to be a very important reference for you, and we're going to refer back to it over and over again. Now we're headed on to the next page, page 3. This is also going to be a reference for you, meaning you need to go back to it over and over again. When we first start learning about quantum mechanical model and the electron configurations, it can be confusing at first, and it helps to go back to our references. So I really want to encourage you to do that. So today, we're going to start off by looking at the energy levels, or we'll say the principal quantum number n. And we're going to look at 4 levels just so that you can see kind of the basics of how they're set up. And then you'll be able to use this as a reference as you go on. So in this case, the 1, 2, 3, and 4 is going to coordinate back to your periodic table here for the first 4 periods, 1, 2, 3, and 4. And remember, periods go horizontally, whereas your groups on the periodic table are your columns, okay? So row, column. All right, so we're gonna use this. I'm gonna kind of keep these together here for us. And we're gonna first look and find out what kind of sublevels are located in the first principal quantum energy level. So here as we go across, you'll see we only have S block. Hydrogen and helium are both in the same color. That color corresponds to the S block. So we're going to say that we have the S sublevel. The way that I would draw this is I would take a 1 from the period number, and then I'm going to say S for S block. And I know from my notes that that only has one orbital. And so I'm going to draw it like this as a square, and I write it right above it. And I'm going to remind myself that it can only hold up to 2 electrons. It could have 1, but it could have up to 2. Okay? So what we might say here then is that for the total number of orbitals here, okay, we have 1 orbital, and I'm going to put in parentheses, that was the s orbital. So I like to say 1 orbital. Okay. And for every 1 orbital, it can have 2 electrons. So 1 times 2 is 2 electrons max. Okay. You might be like, I'm not really sure where she's going. Just hang on with me here for a couple more minutes. Okay, for the second one, I'm going to look at the second period. So that has an S area and it has a P area. And so the sublevels are S and P. So with that, we're going to have the 2s, put my 1 orbital there. And then this is 2, it's still in the second row, but now we're in the P block. So I'm going to say I also have 2p. And we know that the p has 3 orbitals. They're called the x, the y, and the z orbital. So now I only have s and p. There's no d, there's no f. These are the only 2 that I have there. And I'm using this as this number here. I'm using the block letters to tell me what the sublevels are. So 1, 2, and this could be 1, 1, 1, 2, 2, 2. Okay, so the types of orbitals that we have an s, and we have 1 s and 3 p's. Okay, so together, that's 4 orbitals. 1 s, 3 p's. And if each one of those can hold 2 electrons, 2, 4, 6, 8, 4 times 2 is 8 electrons max. All right, here we go to 3. So the 3 has a little bit of a tricky area. And the third energy level is going to have S and P. So here's the S and the P, but it also has a D. Now these are tricky because these electrons at some points have higher energy, and so they get bumped up to the 4th energy level, but they're called 3D. And so if you recall, I had you write 3D right here. And that's kind of a little piece that you need to memorize. Okay, so we have 3s, looks like that. We have 3p, which looks like this. And then we have 3d. Now, how many does that have? Well, it's got 5. Okay, so 1, 2, 3, 4, 5. Now, I'm going to show you a little trick here. So for the S, okay, the S on the periodic table is 2 columns thick. That's because it accounts for 1 electron and 2 electrons. And since the S area can only hold up to 2 electrons, it can only be 2 thick. So here you'll see that the P is 6 columns thick. 1, 2, 3, 4, 5, 6. So that coordinates to the 6 electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. The D area is 10 across, and so they have 5 orbitals to account for the 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that is the 3D. So what do we have here? We've got 1s plus 3p plus 3d, and that equals 9 orbitals. So how many electrons is that? So this is 2, 4, 6, 8, 10, 12, 14, 16, 18. 9 times 2 is 18 electrons max. Am I making any sense? I'm hoping so. All right. Next, here we go. For 4, we have 4s. Okay. We've got 4p. Now remember, I skipped over this one because I've already included it in the 3rd level. But then I have a 4d right here and a d. So this is going to look similar to the 3rd energy level, but instead I'm going to have 4s, 4p, and 4d. And again, I'm going to have similar numbers here, actually identical numbers, in terms of orbitals and electrons. 1s, 3 p's, and 4d. I'm sorry, I should say 5d. Did you all notice that I made a mistake up here? I said 3d, but I should have said 5d. Probably like, she can't add. 1s, 3 p's, 1, 2, 3, 4, 5 d's. 1s, 3 p's, 1, 2, 3, 4, 5 d's. That gives me 9 orbitals. And that equals 18 electrons max. Okay, so this is going to be a good reference for you to go back to in case you get stuck on that. And then let's go ahead and take a look at some of the rules for making our electron configurations and our orbital diagrams. So the first thing is, what did I do with my periodic table? Here it is, called Aufbau's principle. So Aufbau's principle is going to essentially say that electrons will fill from the lowest energy to the highest energy levels. And so I'm always going to say to my students, start at hydrogen. So this is kind of a cool thing about the periodic table. So if you want to describe all of the electrons that are found in zinc, there's a whole bunch of them leading up to zinc. But you start with its first electron, and its first electron is represented by the space where hydrogen is, and its second electron is represented by the space where helium is, and its third by lithium, and its fourth by beryllium, its fifth by boron. And so what you're going to see is you're going to go from atomic number 1 to atomic number 2 to atomic number 3, 4, 5, 6, 7, 8, 9, 10, and you just keep working your way up in order of atomic number. So, a little rule for yourself, always start at hydrogen and work your way to the element you are describing. Remember, we're describing where all of the electrons are in that particular element. So when you get to like oganesson, when you got, I don't know, 100, what is it, 118 electrons, that's a lot of them to describe. All right, the second rule in this process is the Pauli exclusion principle. So that says there is a max number of 2 electrons per orbital, which I think I've gotten that point across. And it says 1 electron is clockwise. So that we make with an upward arrow. And the other is counterclockwise, which is that downward spin. So we like to call this the rule of opposite spin. And this is partly what allows 2 negative particles to be in close proximity to each other and not completely repel. All right, the last rule is Hund's rule. Hund's rule applies only to sublevels, and really it only applies to the P, D, and F sublevels. Okay, so the reason is if there is greater than 1 orbital in a sublevel, aka P, D, or F, then I should put a comma there. The electrons will fill in the orbitals with 1 electron before doubling up. So really before doubling up in an orbital. So you'll notice that earlier, like when I had the p orbital, you notice that I didn't go up, down, up, down, up, down. What I did is with this p orbital, I filled it 1 up, 1 up, 1 up, and then I would go back and fill it this way. And you might be like, well, it doesn't really matter when you have 6. Well, it doesn't, but I try to get in the habit of always doing it this way because if I have any less than 6, which happens quite a bit, I want to have them in the right position because we actually will designate if they're really in the X, the Y, or the Z position. Okay, so let's try a couple of simple ones. The first 2 that I'm going to do some drawings and such on them, but then afterward, anything bigger than this, we're going to make this quite a bit, we're going to not make the actual drawing on it. So the first element is lithium. Okay, and so here's what I'm going to do. I'm going to say lithium has an atomic number of 3. I am going to say, I'm looking at this, it doesn't say anything about being an ion. So there are 3 protons, there's also going to be 3 electrons. And so I have to describe the position of all 3 electrons. So if we had looked at Bohr's model, good old Bohr, he would have had a nucleus in the center, which is extremely small. And then he would have had 2 electrons somewhere out in this first level. And then there would have been 1 out here. So in Bohr's model, it went 2, 8, 8, 18, and that you can see is represented on the periodic table 2, and then there's 8 across, and then 8 across, and then if you also have 3Ds, then it's 18 across. So Bohr's model does actually fit really nicely with the quantum mechanical model, but it doesn't have the three-dimensionality. So for the quantum mechanical model, we would have had to make something like this, nucleus in the center. Then we would have had to have drawn a wonderful sphere here. And in that sphere, we could fit 2 electrons. Now, you guys, this is not so bad drawing this, although I'm a horrible artist on this, making these look like spheres. All of you artists, don't laugh at me, okay? Okay, I do know that there's better ways to do this. But that would have been the 1s. And then outside of this would have been that 2s space. I don't know, can you see that? Yeah, I think you can. This was my 1s space right in here. This is my 2s sphere, and I'd have one more electron somewhere in that space. Already, with only 3 electrons, it's very messy. Okay, the next thing that we can do is called an orbital diagram. And so with the orbital diagram, I actually really like these. What you do is you're going to just follow along with the periodic table, and we can write actually the second part of this, which is our electron configuration at the same time. So we can do both of these at the same time. So again, we start at hydrogen, and we're going to travel along the periodic table until we get to the element we're describing. And by the time we're done, we'll have described the location of 3 electrons. So the first thing I'm going to do is start at hydrogen. Hydrogen always starts at 1, so I'm going to write 1. And then hydrogen is in the S position, so I'm going to say S. And then I'm going to ask myself, how far can I get on the periodic table with just 1s? Well, I can get 1s1, 1s2. So the maximum is 2. So I'll write 1s2. That would bring me from hydrogen through helium. And I'm going to also write that in my diagram here. And that's 1 up and 1 down. 1 electron up, 1 electron down in the 1s. So this and this are very similar to each other. This is a diagram. This is just handwriting it out. Okay, so now I get to lithium. So I went from 1 to 2. So the next thing I do is I get to lithium. And fantastic, we're already at the element we're describing. And so lithium is no longer in the first level, but it's in the second level. So I'm going to say 2. But it's also in the S block. So I'm going to say S. And since I've arrived here, I haven't made it to the 4th spot here. So I only have 1 electron here. So I'm going to say there's just 1. So in my diagram, I would make 2s and I would write it right above it. And I'd only put 1 electron in there. So now you see I have the location of 1, 2, 3 electrons. Here's 1, 2. That's that first sphere. And then the bigger sphere with more energy, which is above it, that's Aufbau's principle, is outside of it here. And here's my potential spot where it could be. So that's our first one. Okay, now let's try another one. Let's go to boron. Boron's number 5 here. I'll put my beryllium letter in here. Okay, so for beryllium, I'm sorry, I just said beryllium, so I said it again. For boron, we can see it has an atomic number of 5. It's neutral in this case, so it also has 5 electrons. In Bohr's diagram, we would have a nice ring, 2 electrons in the first one, and then we would have 3 more, and they would be as evenly spaced out as possible according to Bohr. And then we go to our quantum mechanical model. Oh, this is going to be interesting. So with the quantum mechanical model, we'd have a sphere for the very first one, and this one would be called 1s. Okay, so we're actually just starting back at hydrogen, and we've got to make our way all the way to boron. And so we'd have 1s1, 1s2. So we'd have 2 electrons somewhere in there, and they'd be moving at a very rapid rate. So this is just like a little photograph in time. Now, outside of that sphere, we'd have, okay, so 1s, and then the next thing we hit is 2s. So this is 2s. And again, this would be a sphere, like a big basketball, right, with like a tennis ball inside of it. And I'd have 1, 2, and I still would not have gotten to boron yet. So 1, 2, 3, 4. So I can put 1, 2 electrons somewhere in there. And then here comes the real pain in the butt. Here's the p block. So instead of drawing spheres, I got to draw this stinking thing like this, right? And already you can see this is a pain in the butt. And so this has got the X, the Y, the Z, but it only contains 1 electron. So I don't know, right here. And that is my 2p. And so you can see I've got 5 electrons represented in here, but it is so stinking messy. So this is why we do orbital diagrams and orbital configurations. So let's do the configuration first for this one, and then we'll draw the diagram out. So for our configuration, we're going to travel along our periodic table until we get to boron. So I'm going to say 1s, 1, 2, 2. That represents these 2. I traveled from hydrogen to helium. And now from helium, I go to lithium because I'm just going in order of the atomic number. So now I'm at 2, S1, S2, 2, S2. And then I go from beryllium, that's number 4, to boron, number 5. And now I still am 2, but I'm 2p. And it's just the first one, so this is going to be 2p1. So to make the orbital diagram of this, we start with 1s. Now I'm drawing this like Aufbau would say. You kind of have the lowest energy level. It kind of reminds me of like an elevator. Like this is like the first floor. We can fit 2 electrons there. Then 2s, so going up to the second floor. All right, so 1 up, 1 down. Now 2p is actually drawn slightly off to the side. It's sort of like the elevator here at Berkeley High School. There's like floors, like we have 2 floors, the main floor and the upper floor. But like the upper floor is, and the lower floor both have like sort of like mid levels. So like if you're down at the student center, down by the fish tank, you have to go up a bunch of stairs to get up to the T. And then if you're upstairs at the T and you want to go down to the LMC, you got to go down a few stairs. You're still on the second floor. So this is the first floor and this is the second floor. Okay, so there's only 1 electron there, so that's going to go here. Okay, let's try 2 more, but we won't do the Bohr and quantum mechanical model. We're just going to use the periodic table now for these. And so this one is, the first one we'll do is a very, very, very funny rubber. Does anybody get my joke? A very funny rubber. Silicon. Can you believe it? All right, I gotta grab my other periodic table. Here it is. This is the one I made with you guys. So I've got to find silicon as number 14 on the periodic table. And so I'm going to put that right here. It's kitty corner from from boron. So silicon, it's number 14. Okay, I'll fill in the rest of these: boron, carbon, nitrogen, oxygen, fluorine, neon, and then sodium, magnesium, and then aluminum. Okay, so let's do this. And I think we can start with the electron configuration first for silicon. So it always starts off the same way. You start at hydrogen. Hydrogen and helium together are going to be 1s2. And I go to the next row, 3 and 4. Okay, so now I'm going to say 2s2. Now I'm going to keep going. Now I'm on the second level, 2, but I'm in the P. If I go all the way to the end, I still haven't reached silicon. So 2p1, 2, 3, 4, 5, 6. And we know that a p can have up to 6, a p sublevel can have up to 6 electrons. So now I'm at number 10. I go to number 11, sodium. That's now on the third level. 3, it's in the S block. So I say S, S1, S2, so 3s2. And now I'm headed to, I'm really getting close, 3p, 3p, 3p1, 3p2. Do you see I'm 2 in here? So if I add up all these numbers, 2, 4, that plus 6 is 10, 12, 14, that should equal the 14 electrons for silicon. So every single electron is described. Now, if we want to make this into an orbital diagram, which is really nice and visual, and you will need to be able to read these. And this is the vertical model that I've showed you so far. All of us teachers will be showing you guys how to do a horizontal model. So here's 1s, then I write the 2s right above it, up and down. The 2p just off to the side, just like I was talking about having, it's still on the second level, but it's just slightly higher energy. So we'll do 1, 2, 3, 4, 5, 6, because it's got 6 electrons. Now the 3s, oops, I'm going to write my 3s right here, but here it is on the third level. 1 up, 1 down for those 2 electrons. And then the 3p right above where the 2p is. Okay, but I only have 2, so 1 up and 1 up. See, that's Hund's rule. By the way, I remember Hund's rule by like making this H, and look at my arrows are both pointing up the same way, reminding me they all go up, and then when you get to the end of the sublevel, they all go down. Okay, last one. Let's go to, oh boy, what did we put on here? Chromium? Holy moly. Okay, chromium, here it is, number 24. For crying out loud, what are we? Why did we do this? Because we want you to learn how to do this, of course. Okay. Here we go. Are we ready? Let's do this. Chromium is right here on the periodic table. It happens to be number 24. That means we got to start at hydrogen, and we got to make our way all the way to number 24. Now, I always challenge my students to do number 74, tungsten, which I haven't given you enough information to totally do that one yet. And then eventually, I have students do oganesson, 118. It's kind of a lot of fun. I'm going to be honest with you. It's kind of geeky fun, but it sure is. All right, so here we go. Electron configuration. We have to describe 24 electrons, okay, because chromium's number 24. And we need to describe every single electron that it has. So we start at hydrogen. So it's literally going to start off the same way that this previous one is. So here we go. 1, it's the S block. 1s1, 1s2. That's the maximum you can have anyway. 2s, 2, 2p6, 3s2, 3p6, 4s2, and then now we're at the 3D. Don't be surprised by that, but remember we marked it 3D. And again, memorize that. That's where it belongs, 3D. And then everything, so if this is 3D, 4D, okay, we're going to follow suit with that. This is actually 5D right here and 6D right here. All right, so 3D. Now, how many belong there? 1, 2, 3, 4. So we're going to say 3D 4. So 2 plus 2 is 4, 4 plus 6 is 10, plus 2 is 12, 18, 19, 20, plus 4 is 24. All right, here we go. 1S, 1 up, 1 down. 2S, 1 up, 1 down. How am I doing? I'm hoping you guys are following with me. You're going to do lots more of these with your teacher. Might be me, might be Miss Olson, might be Miss Nixon. Oh, I'm going to run out of room. I just knew it. 3S. Boop, 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 boop. 3P. It's all the way full. 2, 3, 4, 5, 6. Then I've got 4S. Isn't this funny? On my notes, I had plenty of room because I'm live on my camera. I ran out of space. It's Murphy's Law. All right, there's 4S. Now 3D goes all the way over here. So you're going to find out you have a column of S's, you're going to have a column of P's, you have a column of D's, and eventually you might have a column of F's. 3D is going to have 5 across. 2, 3, 4. You make a nice rectangle. 4 lines in between will give you 5 boxes. And we've got 4 to put in here. 1 up, 1 up, 1 up, and 1 up. All right. I feel like I need to make that a little clearer. All right, ladies and gentlemen, I think we have given your brains a little bit of challenge today. I hope that you can use this video, that you can use it as a reference. You can stop it, you can go back, you can ask your teacher questions, and you can get this. You will eventually get it. It does take a little bit of perseverance, but I just want to remind you, you've got this.